Can you hear them? Okay. Now let's look at the other option here for our pipes. We can have an open, closed pipe. So I think the best thing for us to do again is to look at the little app. So this is my first harmonic, the very lowest frequency we can make. This is the very common frequency to have, especially if you're blowing across like the top of a water bottle or something. You're making it have a sound. It's probably the first harmonic. Now the open end is always an antinode. So a closed end is always a node. And now is this one symmetrical? No, so things are going to be a little bit different. Okay? Now how much of a whole wave then is in this pipe at any time? A quarter. It goes from the beginning to the first amplitude. Isn't that a quarter of a whole wave? So for the first one I can possibly make, closed on one side, open on the other, I get a node and an antinode, or a node and an antinode, so that's the other possible position there. And if you reference our little sine curve over here, if you go from a node to an antinode, what portion of that sine graph do we have? It's a quarter. So it's a quarter of a wave. Now, speed is still frequency times wavelength. And our wavelength up here would be equal to 4L. So then our speed would be equal to the frequency times 4L. So our frequency would be V, the speed of what? Sound, over 4 times the length of the pipe. Oh, that looks a little bit different already. So if we go up higher, now I've got to have a node on the closed end, an antinode on the open end, and they have to oscillate or alternate. Okay, so if I've got an antinode, I've got to have a node, another antinode, and a node at the end. How much of a whole wave is inside my pipe at any time now? 3/4. Very good. So the second one I can make has a node, antinode, node, antinode. There we go. It's not very pretty. Looks better. Okay, so think about again in terms of our little sine curve here. We start and we go positive amplitude back to 0 into a negative amplitude. We didn't do this little part right there, so that is 1, 2, 3 parts of the whole wave. So the length of this pipe is equal to 3/4 of a wave. And speed is still frequency times wavelength. And wavelength would be, what, 4L divided by 3? So then our speed would be frequency times 4L divided by 3. So then our frequency would be, what, 3V over 4L? Let's go higher. Oh my goodness. So I still have my antinode at the opening. I still have my node at the closed end. Now how much of a whole wave is in the pipe now? 1 1/4. So is that like 5/4 of a wave? Is that 1 1/4? Okay, so now got a node, antinode, node, antinode, node, antinode. And that length has 5/4 of a wave in it. And speed is still frequency times wavelength. And wavelength would be 4L divided by 5. And therefore the speed would be what? Frequency times 4L divided by 5. So our frequency would be what? 5V over 4L. So let's look at the three that we can possibly make. So the first one we could make was what? V over 4L. The second one we could make was 3V over 4L. And the third one we could make was 5V over 4L. Do we see something that's similar? Do we have 4L in all the denominators? Now, what did the coefficient in front of the velocity mean earlier? It was the harmonic number. Yeah. So, this one could have an understood 1. This one is 3V. This one is 5V. And so what could we say about a general equation for the nth harmonic of an open-closed pipe? NV over 4L. Would that work? But tell me about N. The first one I could make was 1. The second one I could make was 3. The third one I could make was 5. What do you think the next one's going to be? 7. So tell me about the harmonics. They're all what? Odd. We only get odd harmonics with an open-closed pipe. So V is still the speed of sound because it's still air moving. L is still the length of our pipe. And F is the frequency of the harmonic. Now, well, that's all I have to say.